standing by. Today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to Katherine Hamilton. Thank you. You may begin.
Thank you. I'm Katherine Hamilton with NASA's Office of Communications. Teams gathered today to review the overnight operations and the additional analysis requested during yesterday's mission management team meeting in preparation for launch. Teams are proceeding toward a launch on Wednesday, November 16th during a 2-hour launch window that opens at 1:04 a.m. Eastern Time. Here to give us an update on the countdown and launch operations, as well as today's mission management team meeting, are Jeremy Parsons, Deputy Manager for the Exploration Ground Systems Program at NASA's Kennedy Space Center, and Mike Sarafin, Artemis I Mission Manager from NASA headquarters. Jeremy and Mike will share a few opening remarks, and then we'll take questions. Reporters on the line can enter *1 on your phone to be entered into the question queue at any time. Jeremy, we'll start with you.
Good evening. Thank you, Catherine, and thank you for the folks that have interest on the call here. So per plan, the team was on console for call to stations at 1:24 a.m. this morning. Countdown to, so far is proceeding very well, and we are on schedule. So what have we been doing since the discussion in the conference last night? So last evening, we powered up the vehicle. We ran a series of what we call program-specific engineering tests, or PSETs. It's basically integrated vehicle testing, and all was nominal. So it was a very thorough checkout of the vehicle. Everything's looking really good. On the mobile launcher, we're getting panels and valves all configured for cryo loading. We filled the sound suppression and ignition overpressure tank, the big water tank out at the pad. And then we've brought up power on Orion, the upper stage ICPS, and core stage. So they've all been powered up at this time. And we're going to remain with those up for the remainder of launch countdown. We also have been working in troubleshooting of the J8 connector that was discussed last night. I'll give you a little bit more details on that in just a minute. But before I do that, I'm going to go through what you can expect tonight and into tomorrow in terms of launch countdown. So tonight, we're going to begin charging all the flight batteries on the vehicle. We're going to get into pressurizing the core stage composite overwrap pressure vessels. We'll do final walkdowns tonight and through tomorrow, and we'll do a series of comm checkouts with Orion. Going into tomorrow, we pick up with our blast danger area clear at 12:04 Eastern. We get into air to GN2 switchover at 13:14. We clear out the entire launch danger area for all personnel at 2:04, and then we get into the new built-in hold at 14:24. So that's at the T-minus 6 hour 40-minute mark. So when I say it's new, it's the same built-in hold. Previously it was 2 hours and 30 minutes. We have added an hour in for cryo-loading concept of operations changes. Just a kind of a quick level there. So we added an hour basically to do a slower, more gentle LH2 loading procedure. So it adds about 17 to 20 minutes for LH2 chill down and 32 minutes for fast fill. We're also now doing liquid oxygen and liquid hydrogen loading in parallel. So with all that picks up, again, that built-in hold picks up at 14:24, and then we expect the launch director to give a go for cryo loading at 15:24. T0, as Catherine mentioned, is at 1:04 a.m., and we got a 2-hour window fully available to us. So real quick, and then I'll pass it over to Mr. Sarafin. The J8 connector. So team got in late last night. We had already changed out the cable, done a series of ring-out testing on that. We then changed out the ground receptacle side of this, and so that's on the back of the LH2 tail service mast umbilical plate. We did that change out and then performed a series of retests. Team did a really good job wringing out all of the data, determining the wrist posture, looking at all measurements flowing through there, where redundancy occurs, what launch commit criteria are associated with them. At a top level, what we were basically seeing was measurement transients during power-up, so they would go out of kind of expected ranges for a little bit when you first power up, and then they would come back into nominal ranges. We are already in a powered-up configuration on all of the core stage ICPS and Orion, and we're going to remain in that configuration through the rest of Launch Countdown. So all of these are kind of at a normal, stable configuration. That being said, we went through each of these launch commit criteria that are associated with these measurements, determined criticality, redundancy, and what we call pre-planned contingency procedures, which is basically allows us to say we take failures on any of these measurements, say we know we have redundancy in these other measurements, and we are still okay to launch. The unanimous recommendation for the team was we were in a good position to go ahead and proceed into Launch Countdown with these measurements, and that was, again, based off the criticality and redundancy posture that we have. And really, we have a very robust system here with a number of measurements in other areas. So with that, Catherine, I'll turn it back to you. I believe that's kind of a summary of where we're at.
Thank you, and we'll go to Mike Sarafin. Thank you. We'll go to Mike Sarafin next.
Okay, good evening, and thank you again for continuing to follow the Artemis program and the Artemis I mission. This afternoon, we had a launch minus 1 day mission management team meeting. The mission management team met for 1.5 hours this afternoon, and the primary purpose was to focus on 2 special topics. The first was the status of the liquid hydrogen umbilical electrical connector located at the J8 port that Jeremy described, and we went through a status of the connector removal and replacement and the work that was completed, any findings that we had as a result of it, and then the post removal and replacement systems status checks. Right now, as Jeremy described, we don't have any changes to our posture as we head into the launch attempt. The launch commit criteria were reviewed, and we agreed that the as-written launch commit criteria were the appropriate posture to have headed into the next attempt. And that's largely based on the fact that we have systems redundancy as it pertains to the signals that we need to verify as part of those launch commit. The other item that we talked was the one open action that we took out of the launch minus 2 day review held yesterday, and that pertained to the Orion room temperature vulcanization material, or RTV material, delamination that we saw during Hurricane Nicole. On the east side of the vehicle, or roughly in the Orion coordinates, the 270-degree location on the aerodynamic shell called the ogive, where that meets up with the crew module adapter. We had a strip of that RTV delaminate during the storm, during the windy portion of the storm. And the purpose of that RTV is essentially to fill in the gap that exists between the launch abort system ogive and the crew module adapter. There's a small area that exists where the two made up, where we have an aerodynamic barrier, and it could actually cause a little bit of air circulation in there as we ascend through the Earth's atmosphere and cause aerodynamic heating. So to eliminate that little gap, they put this RTV material in there, and it just creates a very flush surface, a very streamlined aerodynamic surface. Yesterday, when we reviewed the status of that particular delamination that we observed and the likelihood of a reoccurrence during flight, we needed a little bit more time to review our flight rationale, and the team came back and we accepted that flight rationale today based on a proven methodology called the 7 elements of a good flight rationale. And we looked across the entire vehicle stack from the Orion spacecraft all the way down to the base of the stack, and we agreed that the risk was bounded by current hazards and hazard reports that we have out there that were established well before the agency flight readiness review, and when we accepted our risk baseline at the agency flight readiness review. So we went through that today, and we closed that action item, and we accepted that flight rationale, and it just was one of those circumstances yesterday where the team needed a little bit more time to assess our overall risk posture and to understand this new issue that had occurred earlier or mid last week as a result of Hurricane Nicole. So we went through that. I asked if there were any dissenting opinions. There were none, and we accepted that flight rationale. So that was the purpose of today's Launch Minus One Day Mission Management Team meeting. We are proceeding to the next decision gate to set up for the November 16th launch attempt, as Catherine indicated at the outset. So there's no change in our plan to attempt to launch on the 16th. The next decision gate occurs tomorrow afternoon at 2:30 in the afternoon Eastern, and that's our tanking decision gate, and we'll get together again as a mission management team. So with that, that was the outcome of our meeting today, and we look forward to the tanking tomorrow afternoon, and I'll pass it back to you, Catherine.
Thank you. We'll now begin our question and answer session and take questions from reporters on the line. Those on the phone can press *1 to be entered into the queue at any time, and press *2 if you'd like to be removed from the queue. Your lines are on mute now, and the operator will open and close your mic when we come to your question. Please identify to whom your question is addressed, and we ask you to please keep it to one question so we can get to as many reporters on the line as possible, and if we have time, we will do a second round of questions. We'll start with Kristen Fisher of CNN.
Thank you both so much for taking our questions tonight. Two questions for you, and I'll try to keep them brief. I just want to make sure that I have it right in sort of, layman speak. Would it be fair to say that these two issues that have given you guys some trouble over the last 24 hours or so, the damage caused by the hurricane, that the the RTV material and this umbilical, that those two issues have been fixed? Or that you all are just now comfortable with proceeding with them as is? If you can just kind of give some clarification as to how we should refer to that, I would appreciate it. And then my second question is, if each of you had to pick one moment in the countdown between now and liftoff that gives you the most heartburn to think about, what moment would that be? Thank you.
Yeah. Hi, Kristen. Thank you for the question. In terms of the two issues that we reviewed today at the Launch Minus One Day Mission Management Team meeting, I would say that we're comfortable flying as is in both of those cases. We did attempt to fully resolve the electrical connector on the tail service mast umbilical, and we're still seeing some funnies on that particular umbilical, but we reviewed the fact that we have redundant data that comes across that interface from the rocket and the spacecraft to the ground side, and as well as the delamination of this RTV material. And then in terms of one moment that would give me the most heartburn between now and launch, yeah, that's a good question. I haven't had time to think about that one. Nothing immediately comes to mind. This is something that it's something we've been preparing for, and we've trained for, and there are a number of decision gates that we have purposely to set up to review our risk posture in the event that something changes, like we saw here as a result of Hurricane Nicole. And I see the team that's prepared to do that. So nothing comes to mind. I don't know, Jeremy, if you have anything to add to that.
Well, kind of given the white dress rehearsals, for me, I'll probably breathe a bit of a sigh of relief after we get into LH2 fast, slow fill to fast fill, right in that time frame. I feel very confident in the procedures that we've worked, but that'll be one of those things where I think it'll be a big milestone once we really get into a steady state fill of LH2, and so that'll be around 4 p.m. or so tomorrow afternoon, and so that'll be something I think we'll all be watching closely.
Thank you. Our next question is from Marcia Dunn of the Associated Press.
Yes, hi. Mike, I'm trying to get a better understanding of the RTV, comfortable flying as it is. Is it that you don't think any more might come off, or if it does come off, that it won't hit the rocket, or if it does hit the rocket, it won't do big damage? I mean, what's your thinking along the lines of risk in that regard? Thanks.
Yeah, Marcia, that's a great question. There is a small likelihood that more RTB would come off the vehicle, but we do have flight rationale that supports that. In order to have an issue in flight, first of all, we need additional RTB to be released, and then it needs to impact part of the vehicle, and that vehicle element has to seek what we call critical damage, and there are limited components that could be exposed to that just due to what we call debris transport and where these objects are relative to where the RTB would be liberated from. So we look at things like, is this within our experience base? Are there self-limiting aspects of this particular material and material release? And we do have self-limiting aspects, like the fact that it is going to tear because it is very pliable, and when it gets into the airstream, it's not going to come off as one really long piece. It will basically break into smaller pieces. And then we do know that this particular material has a very low lift coefficient when you look at it aerodynamically because of how pliable it is. We actually had a witness sample in the meeting today. It was about 12 inches long, and I believe that we've also posted photos online of where we've lost the material for the general public to help understand what the material looks like. And it is very thin. It is relatively lightweight, and it is very pliable. And this low lift coefficient, the fact that we have a physics-based explanation, the fact that it has self-limiting aspects, the fact that we have an experience base of flying with this material, and not just on Orion, but with other programs. RTB is a very commonly used aerospace material, but we also flew Ascent Abort Test number 2. We flew Exploration Flight Test number 1. We had RTB in a very similar area in both of those test flights, and we did not see material at this same interface liberated during the aerodynamic flight there. So we do acknowledge that there is a non-zero chance that we could have additional liberation of RTB in flight, and that there is a possibility that it could impact a different area of the vehicle downstream of Orion. We know what those areas are. We looked at it all the way down the stack. The most likely area to have the RTB impact the Orion vehicle is on the launch vehicle stage adapter. And the launch vehicle stage adapter is a very tall conical feature that sits between the top of the core stage and the base of the interim crawl propulsion stage. And it literally takes the diameter of the Orion spacecraft and extends it out to the much larger diameter of the core stage. And just the fact that much larger area is there, that becomes the most likely area. The LVSA is a very robust piece of hardware. It weighs about 10,000 pounds, and it is used to translate the 8.8 million pounds of thrust at liftoff of the boosters and the RS-25 engines up into the upper stage, the interim crawl propulsion stage, in the Orion spacecraft that sits above it. So it translates 8.8 million pounds of thrust up into a spacecraft that weighs over 70,000 pounds, and I don't remember the mass of the interim crawl propulsion stage, but we're talking tens of thousands of pounds there as well. So the launch vehicle stage adapter is a relatively inert piece of hardware, and that's the most likely. It's simply a structural adapter, and that's the most likely area that it could be exposed. But there are other areas that we looked at, again, because of the particular material type that we're talking here, and other risks that we have disposition in the past or have in our hazards, like ice and the thermal protection system on the core stage. We considered this to be bounded and within an acceptable range of risk. So that was our flight rationale.
Thank you. Our next question is from Bill Harwood of CBS News.
Yeah, hey, thanks. I'd just like to follow up on Kristen's earlier question to Jeremy. what do you think the odds are with or I don't know, I'm not asking you for odds, but how confident are you that when you get into fueling that you won't have to do manual adjustments like you've had to do in the past, with pressure and flow rates and temperatures management? I mean, how confident are you might be able to just load the fuel and go? Thanks.
Yeah, hey, Bill, I appreciate the question. And, what I would say is we absolutely verified and validated these procedures during what we did was a tanking test following launch attempt number 2. And so what we did there is we spent a lot of time looking at what is the environment around these quick disconnects, what does the seal look like, what are the pressures we're putting on there, and then the associated leak rates. I would say at this point in time, we are more confident than we have ever been in our loading procedures and how to do it in such a way that puts the least amount of pressure on the seals and to really try and keep it quiescent. The other thing is we have a purge can, right, basically around these quick disconnects where, we try and remove, we purge it consistently with helium. And so, and we have hazardous gas measurements kind of coming through there. We've talked with all of our requirements, and we're allowed to have, a momentary transient as we, up pressure, because, again, you don't have any, it would just be for a short time period. And that's really the worst case that we saw during this tanking test was you saw kind of a brief spike of hydrogen when you introduced, more than a couple of PSI worth of pressure, and then it quickly came down. And so we've accommodated for all of that in our test procedures and in our safety requirements. So feeling pretty good right now about that kind of going into it.
Thank you. Our next question is from Nell Greenfield Boyce of NPR.
I'm just wondering how you all are feeling. There was a huge amount of attention back in August, and then there were all kinds of things that have happened, the faulty sensor, fuel links, Hurricane Ian, Hurricane Nicole, and, here you guys are again. I'm just wondering, Jeremy, could you tell us, does it feel real now? What's the feeling of the team? Is it like Groundhog Day? This isn't a very elegant question, but I guess you know what I'm asking here.
I know it's a good question. What I'll tell you, if I step back, what I feel is extremely proud of the resilience of this team, and what I would tell you is for all of us, right? It was a bit of a letdown when we had to roll back for Hurricane Ian. What I was so impressed with is the team turned around. We were kind of down that night. Then by the next day, everyone was super focused on what work we needed to do, to get back out at the pad, and then it was a similar story for Hurricane Nicole. By late afternoon, the day after the storm left, we had completed all walkdowns, we had completed imagery. Any issues were largely behind us. I mean, I will tell you, the team is firing on all cylinders at this point, and so I just can't be more proud of them, because I think if you would have asked me a couple of weeks ago, we would go through a storm like Hurricane Nicole and then be able to turn around and have cleared the vehicle and be in good shape. I would have said, hey, chances are probably low, but this team has really just been firing on all cylinders.
Yeah, and Nell, I would add that the word perseverance comes to mind. The team has had to persevere through numerous trials, and that perseverance in turn has developed character in the team, and that gives me comfort that we're going to be ready when it's our time to fly. As our administrator said, we'll fly when it's right, and Administrator Nelson he stands there with us, understanding that we've got to get this right. And in spite of the challenges that we've had, the hydrogen leaks and the storms and the other technical issues that we've had, the team has done a great job. And as Jeremy indicated, they've persevered through a number of situations. And our time is coming, and we hope that is on Wednesday. But if Wednesday is not the right day, we will take that next hurdle, that next trial, and we'll persevere through that.
Thank you. Our next question is from Joey Roulette of Reuters.
Hey, thanks. I just had one follow-up on the RTV issue, I guess for Mike Sarafin. What other risks does this present that doesn't have to do with the potential for debris hazard? What does this, I guess, mean for the aerodynamics during, ascent? What kind of forces are you guys going to expect to see now that a lot of the RTV is now gone? Thanks.
Yeah, Joey, that is a good question. We did review the aerothermal and aero heating aspects of it, knowing that we had a portion of the RTV on the currently east-facing side of the spacecraft, and because we already have an aerodynamic barrier that sits there, our aerothermal models and the analysis the team has done shows that there's not an issue there. This was just a way to reduce the aerodynamic turbulence and flow in that particular area, but we're within our allowables. In terms of other risks that we talked through, that and debris liberation were the two primary areas that we focused, and really nothing else comes to mind in terms of what we needed to address. It was just the debris liberation flight rationale that we needed a little more time to go resolve. But all the other aspects of the risk were characterized yesterday, and we understand that. So, but I would say that really covered the gamut.
Thank you. Our next question is from Irene Klotz of Aviation Week.
Thanks. This is for Mike. Does the RTV issue change the original loss of mission odds? I think you told us it was 1 in 125 back in August. And also for Jeremy, do any of the changes that you're making to the fill affect the 489 launch commit criteria? Any more, any less? Thanks.
Yeah, Irene, in terms of the loss of mission or loss of mission number, or the 1 in 125, which is the loss of vehicle number that was quoted earlier, and we assessed as our risk baseline at the agency flight readiness review. Again, if you look at maybe a couple of decimal points past that 1 in 125, there's probably a marginal increase in risk due to the potential for the RTV to be liberated and then follow a very specific trajectory and hit a very specific component and cause what we call critical damage, which would essentially result in loss of functionality. We see that as a low likelihood, but there is a chance there. So in terms of changing from 1 in 125, there's no material increase there. But if you were to go several places after the decimal point, I'm sure there would be an increase. But we consider that an acceptable delta to the risk. And that is the purpose of the mission management team, is to review any changes from the risk baseline at the agency flight readiness review, and we did that today, knowing that we had the storm cause some of this RTV material to come off, so we had to assess it from an aerodynamic and aerothermal perspective, knowing that we did not have this there, but then also went through the hypothesis that more could be liberated during the ascent phase, knowing that we had some nonconformances there from the storm. So again, I would say there's no material change in that 1 in 125, and I'll let Jeremy answer the second part of your question.
So, Irene, in terms of LCCs, I will have to verify. I don't believe we changed any LCCs as a result of the loading procedure, but I will verify just so I'm not giving you kind of any bad information. At a top level, it doesn't increase our risk posture. The primary downside with kind of the longer LH2 loading procedure is just additional commodity usage, and what we put into place was careful analysis to make sure we can get through the load, get through the full 2-hour window, and then we have a full replenishment schedule in place in the event of a scrub. And so that's just basically orchestrating along those lines. And really, after a couple of those wet dress rehearsals and initial attempts, we have a very, very good feel for our models on commodity usage. And so that was the primary downside by extending that out.
Thank you. Our next question is from Jeff Faust of Space News.
Good evening. Question for Mike Sarafin. You mentioned the launch vehicle stage adapter is the most likely component that might be hit by any RTV material that delaminates during flight. What are examples of less likely but potentially more serious impacts? Are there other components that are more vulnerable to an impact that might cause some of the critical damage that, while unlikely, is potentially theoretically possible?
Hi, Jeff. Thanks for your question. Yes, we did look at less likely areas. Again, if you look kind of nose on at the rocket as if it's literally flying right at you, and you have this RTV at the nose of the rocket, and a piece of it were to come off, you need to look at the surface area that's downstream, and as a piece comes off, really the only area or time frame that we're exposed to having enough energy where the mass of any RTV, if it were to follow a very specific trajectory and impact the vehicle downstream, is in the Mach 2 to Mach 3.5 range, or about 80 to 100 seconds in the flight. So now if you look at it, that's your narrow window of exposure where you have enough energy, where the rocket is accelerating fast enough, but there's enough atmosphere to slow down anything that comes off enough that you have enough impact energy. The areas from highest probability to lowest probability were on the launch vehicle stage adapter, simply because it is a large diameter change from the diameter of the spacecraft to the diameter of the core stage. The next most likely area were the inner areas of the boosters, the solid boosters, and when I say the inner area, the areas that are closest to the core stage, because if you're looking at the far side of the boosters, the ones that are pointing away from the core stage, there's no risk of this RTV impacting the booster. So booster was considered moderate relative to the LVSA. And then the core stage and the interim cryo propulsion stage were seen as low probability. There were some specific areas on the interim cryo propulsion stage that we looked at, specifically the systems tunnels that are small aerodynamic protrusions where we run some wires and cabling up the sides of the stage. And then similarly for the core stage, there's cable trays and some systems tunnels there. The boosters were considered moderate probability, mostly because of some very specific areas. The separation motors at the very base of the booster that are used to provide the separation function. So those were the areas that we looked at. All of those, again, were enveloped by other known debris sources and other hazards and risks that we had. We just needed a little bit of extra time to take this previously, or the RTV delamination that we saw from the storm, and we wanted to verify that was within our experience base, and we did that today. I hope that answers your question.
Hey, just one quick go back for Irene. I did verify there was no changes to any LCC as a result of the LH2 loading procedures.
Thank you. Our next question is from David Curley of the Discovery Channel.
Thank you very much. Mike Sarafin, we've been doing these calls for 18 months now. We've gone through the green run. We've gone through tanking tests, a couple of launch attempts, a couple of storms, hydrogen leaks. It seems, and this is a terrible question to ask an engineer, and I'm sorry, it seems like you're in a good spot. What does your gut tell you? Are you going?
David, I'll know the answer to that question, in the early hours of Wednesday, the 16th, if we're going to go. We are going to set up, and we're going to do our best, and we're going to try on Wednesday. That said, if we have an issue that occurs that would cause us to meet one of our no-go criteria, it may not be our day. As I've discussed before, we really have three buckets of criteria that could cause us to be no-go. Our launch commit criteria, our technical must-meet criteria, the 489 launch commit criteria. We have range safety criteria in the interest of public safety, and if we had somebody out there or a situation that there was a range safety risk that was not handled or managed, we may have to halt. And then weather, relative to meeting our weather criteria. On Wednesday, we have a very favorable weather forecast. We've seen very favorable weather forecasts turn into no-go conditions in the past. I hope that's not the case, but we've also seen very poor weather forecasts turn into a go and launch. So, the answer to your question is like trying to predict the weather or predict, whether we're going to meet all these technical criteria. We're going to go when it's right, but we're going to give it our best shot on Wednesday, and we're set up to do that. I'm hoping that all the systems line up, the weather lines up, and the range lines up, but we're not going to commit this vehicle until it's time.
Thanks. Our next question is from Chris Gebhardt of NASA Spaceflight.
Hi, yes. Two quick questions here. From the fueling test on September 21st, you allowed the ambient LH2 concentration limits to go up to as high as 10% with really strict monitoring on that. And I'm wondering if that's the case for Wednesday, or if the limit is back to 4% with the option to increase back up to 10% for troubleshooting purposes, since you have the data from the September test on that. And then also back to the RTV issue, I guess I'm having trouble wrapping my head around this. If Nicole, with winds of 75 miles an hour, liberated this, doesn't that tell you it would have come off as soon as the local airstream reached speeds greater than 75 knots? And how does that factor into the discussion of a low chance of more RTV liberating, given the speeds that SLS will be accelerating through the dense lower atmosphere at? Thank you.
All right, Chris, so to answer your first question, so that 10% is within the purge can around the quick disconnects where we actually, do the fueling of the liquid hydrogen. And so we are going to keep those same constraints that we put on there for September 21st. And so that 10% isn't remains at 10%. It would be, again, kind of that transient. As you increase pressure, you might see a small spike of LH2 that quickly comes down. And so rather than have it automatically go into a revert flow, stop and revert flow sort of condition, again, we are going to allow that 10% for a small period of time until the pressure kind of equalizes. So we are going to keep that in there, and I think we found that is going to be beneficial. And
Chris, as it pertains to the RTV delamination from tropical or Hurricane Nicole, with winds that were 70-ish knots relative to the launch profile, we have flight experience flying Orion, both on ground test or suborbital test, as well as an orbital test. Exploration Flight Test 1, I was the lead flight director for, and we launched an Orion spacecraft up to 3,600 miles above the Earth. We did not see anything like this on that flight. And then on Ascent Abort Test 2 in 2019, which was a test of a Orion launch abort system with this same interface, we did not see any material come off. We have to remember that as we launch a rocket, we go from 1 atmosphere on the ground, so the air is very dense at sea level, and the farther you rise up through the atmosphere, it gets less and less dense. And by the time you get to 30 to 40,000 feet, you have enough air up there to support an aircraft that can cruise at cruising altitude. But when you get much more above that, it's really hard for anything to fly aerodynamically, and you have to have a highly specialized aircraft there. So that means your atmospheric density gets very low, and when you map the atmospheric density against the speed of the vehicle, that shows that we have a narrow window of risk relative to any additional material that could come off of this RTV if it were to delaminate. But the fact that we have the other roughly 270 degrees of the 360 degree circumference of the spacecraft out there, where we haven't seen any issues from the coal. We have the flight experience. We do have flight rationale that supports even if more material were to come off. And again, there's a small probability that more material could come off, but not all of it's going to come off. That's why we're not particularly concerned with the risk profile here, because it's enveloped by other experience that we have.
Thank you. Our next question is from Micah Maidenberg of the Wall Street Journal.
Hey there. Hey, Mike, could you just briefly, remind me about the advantages of using liquid hydrogen as a fuel for space launches, in combination with liquid oxygen? I've done various research and interviews and so forth, but just for all the discussion, we've been having over the last few months about it, just remind me, what are the advantages of it? Why NASA's using it here?
Jeremy, you want to take a crack at this one?
I mean, so from a ground perspective, right, liquid hydrogen can be slightly more difficult. What this vehicle has been absolutely optimized for is putting mass into lunar orbit, right? And so that's what you get with liquid hydrogen is very robust performance in getting mass around the moon. And so, this vehicle was designed for deep space exploration. It wasn't designed to put satellites or vehicles into low Earth orbit. It was designed for kind of deep space exploration. And so what you get with liquid hydrogen is the best performance around that, along with a lot of history on the RS-25s. So, Mike, that's kind of my initial take.
Yeah. No, I think you hit it, Jeremy. Liquid hydrogen or hydrogen is the smallest material on the atomic chart, but it has incredible performance or energy density when you compare it on a mass perspective. How much does your fuel source weigh compared to the amount of energy stored in it? And that's why hydrogen is the primary benefit.
Thank you. Our next question is from Lucy Aborge of AFP.
Hi, thank you. Just a quick question on the status of the CubeSats, the 10 CubeSats. We were told that 5 of them were recharged and that the others couldn't. So just decide the time passed, do they all have a chance for a successful mission? Can you just confirm that they all have a shot at achieving their mission? Thank you.
Hi, Lucy. Mike Sarafin. Yeah, we did top off the batteries on 4 of the 10 CubeSats during the rollback to the vehicle assembly building. And in terms of battery state of charge, there is one CubeSat that we know has a low state of charge that may impact its ability to achieve its mission, and the other ones all have sufficient state of charge that of the 10 where we expect them to meet full mission duration. So we did look at that as part of our flight readiness review, and then most recently as part of the our Delta launch readiness review. And there's only the one that we're concerned with, which is a science mission that's looking to map the lunar volatiles around the moon. But the rest of them, we expect to have a adequate state of charge on the batteries.
Thank you. Our next question is from Jim Siegel of NASA TechNet.
Thank you for taking my question, and forgive me if you've covered this topic in a prior news conference, but I'm curious about the content or the cargo in the Orion spacecraft, and was there an attempt to add to the weight of Orion so that it would be about the same when it was launched with crew? Thank you.
Yeah, Jim, thanks for your question. We have a slightly lighter Orion spacecraft than we will have on a crewed flight because we don't have the crew plus all their gear, but we do have mannequins, or moonikins as we've called them. 3 of the 4 seats have mannequins in them, and they mimic the weight and seating locations of 3 of our 4 crew members, so we're missing our 4th crew member from a mass standpoint, but also all the stowage, the food, the clothing, all that other materials that astronauts would normally take with them, we do not have. That said, we do have a series of mass simulators in the vehicle. We do have a series of payloads that we're going to round trip in the Orion spacecraft. We have a biotechnology experiment that we're going to round trip with a number of organisms that we've shared the content online about. We do have a technology demonstration payload that we're flying in the cockpit called Callisto that we're excited about in terms of having essentially a hands-free cockpit. We do have active and passive radiation dosimeters that we're going to gather data on to help inform the flight environment as we fly out of the low Earth orbit, which is enveloped by the Earth's magnetic field, and fly out through the Earth's Van Allen radiation belts, where we have concentrated areas of radiation from deep space, and then out into the deep space environment where we do not have any shelter from the Earth's magnetic field, fly about the moon, and then return back through the Van Allen radiation belts, and then back into the Earth's magnetic field. We're going to gather baseline data on what our astronauts are going to experience. So we do have a number of payloads and science experiments that we're going to use as we go along. We also have what we call the official flight kit, where we're round tripping certain artifacts, either that are representative of our partnerships, and we've shared that information online as well. We have our zero-G indicator, Snoopy, through our partnership with the Schultz Foundation, who have been staunch advocates of our spaceflight program. I wore my silver Snoopy this week to our launch readiness review as a symbol of flight safety. So we do have silver Snoopies on board this vehicle, and it will be quite a privilege to receive one of the silver Snoopies as a sign of support for flight safety to anybody that gets a silver Snoopy that's been around the moon. So those are some of the content and cargo on board the flight, and some of the reasons that the spacecraft's a little bit lighter, but is certainly representative of what we expect to fly on future flights. The spacecraft weight is right around 70,000 pounds. This is a big, heavy spacecraft. After we jettison the launch abort system, the spacecraft weight will be about 58,000 pounds, and then what will splash down the ocean will be right around 20,000 pounds. So we got a big Orion.
Thanks. Our next question is from David Denault of About Space Today News.
Mike, I may have missed this somewhere, but the rocket was facing obviously in the eastern direction, so you had the direct wind hit. How much of the spacecraft were we talking 3 feet or maybe some meters? How much of that was actually lost? And my second follow-up on this, if this were a critical issue and you had to roll back to the VAB, you said this would take a lot of extra time for this material. If you had to do the whole spacecraft, how long would that take?
Yeah, David, thank you for your question. In terms of how much of the RTV material was lost at the pad as a result of Hurricane Nicole, it was isolated to the windward side, so the direction that the wind was blowing from, which was basically facing the beach or the eastward direction. If you're looking at it from the Orion coordinate system, it was kind of centered on the 270-degree location. It was in total, it's about a 10-foot long strip. We know that it was not released all at one time. We have video of confirming that because of the pliability of the material and again because it has a very low lift coefficient, that it has self-limiting aspects, and it literally tore off in little strips as the wind grabbed it and created a little bit of lift. So we know in total it was about a 10-foot strip that was released in pieces. In terms of how long it would take, I don't remember commenting on how long it would take. We do not have access at the launch pad to repair this particular location, but it would take the time to roll back, gain access in the vehicle assembly building, time to apply the material. It also requires a curing, kind of like when you put caulk or paint up, it requires time to dry. And then we would have to remove access and then roll back out to the launch pad. So there is a finite amount of time it would take to do this. That really did not factor into the flight rationale or risk acceptance discussion. The risk acceptance was strictly based on, do we understand what's going on here, and do we have flight rationale?
Thanks. We've got time for a couple more questions. We'll take the next one from Jim McKenna of Aerospace Tech Review.
Thank you. This one is for Mike. The leak on the LH2 line, the last time, if I recall correctly, was caused by a valve command error that led to the line getting overpressurized to 60 psi. What has been changed in the procedures to prevent an occurrence of that type?
Yeah. Hi, Jim. I'll start, and Jeremy can add anything here that I may have missed. But we don't know definitively that the inadvertent overpressure of the liquid hydrogen line at the start of launch attempt number 2. We don't know definitively that was the cause of the liquid hydrogen leak at the 8-inch quick disconnect. What we do know is that when we demated and reviewed the seal at that quick disconnect, that there was evidence of, we know that there was an indentation on the seal, and it was consistent with either ice or foreign object debris. We did not find foreign object debris, and we did run a fault tree to assess potential causes of the hydrogen leak, and moisture, ice, foreign object debris, and then what we call thermal shock were on the root cause, but we could not get to a definitive root cause. That said, we did implement some procedural actions and corrective actions, as well as trained and some additional automation of the software associated with the hydrogen loading operation. So we looked at all the potential causes. We mitigated them to the extent that we could through things like removal and replacement of the quick disconnect, inspection for foreign object debris. We wiped down the surfaces. We automated the loading operation to the extent possible. We improved some of the training. But again, we could not definitively say what the root cause was. I don't know, Jeremy, if you have anything to add to that.
Yeah, I mean, I would just say, the console operator in this case, I mean, he was very experienced, incredibly proficient at what he was doing. What we had done is between launch attempt number 1 and number 2, we had changed a number of the procedures, and going into that, you had to do a number of commands all at a time. What we've done since then, because again, that increases possibility of error, is we basically put controls where on the command console, you basically can only command one of those things at a time, and everything else is locked out. And so that goes along with the procedure, and so they've done a really good job going through, eliminating possibilities for basic error along those lines when you're sending a bunch of commands, and then they've essentially automated the vast majority of it. We're also, again, in this case, when that command was sent, we didn't violate the what we call ICD, or essentially the requirements, specifications for that specific PD, but you still did get a pressure transient. And so what we're really focusing on, and what we validated during the tanking test, was kind of a very slow, methodical raising of pressure incrementally over a long period of time that then really decreases any of those pressure transients on the quick disconnects. And so, again, that was validated, and we're utilizing the same procedures that we did on that September 21st test.
Thank you. We probably have time for just one more question. We'll take a question from Ken Kramer of Space Up Close.
Hi, thank you for doing this, and good luck with the launch. I would like to ask about the rolling back Artemis. Can you talk about? You said it was riskier to roll it back and have it on the ground versus being on top of the pad. Why is it more risky on the ground rolling it back versus or stopping there versus keeping it on top of the pad? Thank you.
And it's a good question. So I think kind of one way to start is that the analyzed loads seen during Hurricane Nicole were less than what the vehicle sees during a roll out and roll back. And so kind of at a top level, those are some of the higher load cases on the vehicle whenever you roll in and roll out. And so that was one thing. There was a couple of things in the decision. We are single string on the crawler transporter, which means you basically only have one crawler transporter. While it is very robust and we have spares and we have a number of things along those lines, if we began to roll back and winds were expected to pick up within, I don't remember the exact time frame, but there was a window where the winds weren't expected to be high, but then they quickly picked up. So if you rolled back and then you had a shoe on the crawler fail or a propeller motor or something like that, there was a not insignificant chance that you could be on the crawlerway when winds exceeded your requirements or lightning rolled in. And again, when you kind of looked at what were the worst case expected conditions out at the pad versus potentially being stuck on the crawlerway, those were some of the decisions involved in the risk trade there in terms of writing it out. We did look very carefully at what were the worst expected conditions and ensured we were well within our design envelopes for all of those cases.
Yeah, Jeremy, I think you said it really well. Ken, obviously the best place to be in a storm is in the VAB. The second best place is at the pad. The worst place to be is stuck out there on the crawlerway. And as Jeremy outlined, we had a risk versus risk trade, and there was some uncertainty in the forecast. And we know that the loads that the vehicle could handle by design at the pad, just sitting there at the pad hard down, are higher from a wind standpoint than if we're rolling, because you need to account, when you're rolling, you need to account for the loads. The analogy that we've discussed is just kind of like, being in a pickup truck going down a bumpy road. When you're on the crawler way, you do impart loads on the rocket. Granted, you aren't moving very fast, but there are loads there. And you need to subtract that out from any wind conditions that you're going to see, and the winds that were forecast at the time, the time that we could roll back in that time frame, were in the range that we thought we had more margin from a vehicle structure standpoint, staying at the pad and riding it out than rolling back. And if we rolled back, we would be accepting the risk that we could have a problem with the crawler transporter during that time frame and be stuck out there on the crawler way and not make it back to the vehicle assembly building. And it sounds like a relatively simple and relatively straightforward thing to do, but it is not. This crawler transporter, if you've ever walked up to it and seen it in person, you feel very, very small. And that is without the rocket, 32 stories sitting on top of it, or with the mobile launcher. The mobile launcher itself weighs 11 million pounds. The rocket's dry weight is a little over 2 million pounds. So when you roll the entire stack, the mobile launcher with the Orion spacecraft and the Space Launch System rocket on it, on the crawler transporter, you've got tens of millions of pounds going across the ground, and again, it was a risk-on-risk trade. It was not an easy decision. It was a fairly long discussion that we talked about, and we did not take that decision lightly. But those were some of the factors that went into it.
Thank you. That is all of the time that we have for questions today. Thank you all for joining us. You can listen to a replay of this teleconference online shortly by visiting the Media Resources tab at nasa.gov/Artemis-1. And join us tomorrow for our launch coverage, which begins with NASA television coverage of tanking and commentary from inside the Launch Control Center, beginning at 3:30 p.m. Eastern. And you can follow along at our blog for updates about the mission as well at blogs.nasa.gov/Artemis. With that, thank you for joining us.